Thoughts and mental operations, whether conscious or not, including acts of volition as well as acts of imagination, are realized in neural activity. Since thoughts can be very fast, whatever the neural realization of thoughts is, has to also be very fast, at least as fast as a thought. For example, I can ask you to recall something that has a unique solution, and you can answer me incredibly quickly. Look how fast this happens. Ready? As fast as you can, say out loud the maiden name of your mother. Boom. Within a fraction of a second, most of you produced her name. Think of all the steps that went into this. Your auditory system decoded the sounds. After numerous steps of analysis, you understood a question. Then your brain commanded the recall of her name from your memory stores, almost surely involving processing in the hippocampus. Upon recall, your brain controlled the muscles of your throat and mouth so that you then said her name. There were easily dozens of steps of neural processing that went into your production of your mother's name, all in under a second. Each step probably lasted on the order of tens of milliseconds. This is amazing. What's more amazing is that you can volitionally generate possible solutions to an open-ended problem almost as fast as recalling a fact, like your mother's maiden name. For example, say the name of a politician out loud. Well, you just said some politician's name, but many politicians were also nameable by you, so there was no singular solution, as in the case of your mother's maiden name. Again, it's amazing how fast you could do this. I can add additional criteria that need to be fulfilled. Now, name a European female politician. No problem, you can do that too, even though I constrained the possible answers by 3 separate criteria: woman, European, and politician. So, whatever the neural code underlying neural information processing is, it not only has to be at least as fast as the thoughts that it realizes, it has to permit the setting of arbitrary criteria that can be met in multiple ways, all within a fraction of a second. In the coming sections, our goal is to understand the basics of how neurons might realize the rapid setting of criteria. Our goal is to understand the basics of a neural code that could realize the kind of criterial causation that I argue underlies the kind of a constrained indeterminism in the brain that could underlie free will. It turns out that neural information processing involves a delicate interplay between excitation and inhibition, where timing or temporal phase relationships are of the essence. By way of analogy, think of excitation as analogous to hitting the gas when you drive your car, and think of inhibition as hitting the brakes. You need both abilities in order to reach your destination. If you had only brakes and no gas, you would not be able to drive. But if you had only gas and no brakes, you would probably crash and burn. So you need both to function in a controlled manner. Similarly, if you could only inhibit neurons from firing, you'd have no firing at all, and therefore no ability to process information using the medium of well-timed neural firing. This would be like coma. There's not much information processing possible in a state of coma. On the other hand, if you could only excite neurons to fire, you would have lots of neural firing that carried no information at all. This would be like what happens in epilepsy, where, again, information cannot be processed because the firing of neurons is arbitrary and out of control, carrying no information. So in a sense, neural processing in the brain walks a narrow ridge between 2 valleys of information processing death. One is the valley of too much inhibition, or coma, and the other is of too much useless neural firing or excessive excitation, which is like epilepsy. Just as in driving, we need the well-timed interplay between excitation or hitting the gas and inhibition or hitting the brakes. Here is a common neural circuit seen in the brain. It involves a neuron that fires. The signal is carried down the axon, but in addition there's a collateral axonal fiber that excites an inhibitory interneuron, which then in turn inhibits or hits the brakes on further firing in the first neuron. This guarantees that the first neuron can send a signal to other neurons downstream, but once it has done so, it's shut off and does not fire again and again, sending the same information or no information that is of any use. It is this fine interplay between excitation and inhibition that allows us to catch a ball, to smile, to think, and yes, to have free will.